Alright, time for another DraftPhysics.com video presentation. So we'll make this a YouTube video. It's been a while, update video. So have made a few videos, mostly on kinetic energy, and so the last one was called Weight Equals, and I'll probably talk some more about weight and how it just, you know, it is everything in terms of how the universe works. Everything's just pressure being applied. Force gives matter the capacity to apply pressure, weight. And without the force, you don't weigh anything. You don't have any mass, you know, in free space because there's no differential in the pressure. There's as much gravitational influence created on one side of the universe as there is the other, for example. And if there isn't something local that changes that, you'll, generally speaking, just stay where you are because you're being pushed equally from both sides. Anyway, then there was believers in relativity. Don't exactly know. I mean, the relativity stuff just comes in terms of the relative motion is understood. If you allow collisions, you can understand that you can do experiments that'll tell you who's moving and who's not. Yeah. Then there's comments on kinetic energy and pendulums and how they work, and this silly concept of inertia they keep talking about, which I've already pointed out. There's nothing saying I won't move. Nothing has anything called inertia. And then they've converted the word even more specifically, and they think inertia is about rotation, and all the rotation comes out of basically some other movement. So the pendulum kind of demonstrates you have a definite force down, and yet the pendulum at its apex, at the maximum swing, so to speak, in that gravity, converts all of the momentum into momentum in a direction, not down, but this way or that way. Clearly pointing out a lot of things, that you can change the direction of a force or energy without it costing you anything. It doesn't cost any energy to do that, or not much anyway. And it also, in my opinion, clearly just demonstrates that the force is time dependent also, but whatever. So that's where all these were. And then the last YouTube video was the Veritasium video, which I was surprised there were a few other people that commented any further in the discussion, in the debate. And I'd argue partly, I guess, because everybody's contriving agreement when the basic premise of his video is electricity goes through a wire by induction, and it really doesn't. The induction is a symptom. It isn't the cause. It isn't the first act. So it's just a wrong, it's just wrong to say there's something wrong with using mechanical models of electricity that sort of diagram the fact that what you're really pushing are electrons. But anyway, you're moving electrons. That's the definition of electricity. That's why electricity has to go through a wire. It has to go through a conductor. It's because it can't happen unless it has a conductor. It has to have something to allow the electrons to do the exchange. It has to have an ordered row of electrons to push upon. It has to have the rope. It has to have the conductor. It can't, you don't have electricity without it. And sparks demonstrate that even in thin atmosphere you still have some pathways that are conducting the electricity. And they're just conducting it through such a small conductor that they're basically burning the atoms, and that's why you see the electricity in a spark, is because the atoms of the conductor are being ionized. They're being vaporized in a sense. Alright. So we'll go to some comments, and then I'll do my thing. I guess that'll be the order we go in. Alright, I'll be back. Alright, so the first question, I guess down here, we'll do first, how do you explain quantum entanglement? So of course I've been over this in videos. There's no such thing. So the experiments that demonstrate this crap, okay, are dependent on the silly idea of basically putting photons through two mechanisms that split them. Alright, and so the first one is a crystal that produces the, you put in ultraviolet light and you get, infrared photons out, two of them. And clearly, I mean, it's just clearly logical that you would surmise that they're oppositely polarized photons. So you're just taking a frequency of 50 and you're saying I can make two 25s out of that. Just making, say it's dot, 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 dot. You're making one dot go left, one dot go right, one dot go left, one dot go right. And you can understand that you can take the 50 and make two 25s really easy. So, and the fact that it's a crystal means the atoms are in alignment. You're shooting the light through at a direction, which means you're probably just wobbling an electron this way. It's sending the energy this way and this way as it wobbles. And it's splitting the energy of the original pattern into two new patterns that would have opposite polarization. One of them would be on when the other one's off. So you created your left and your right-handed glove. So aren't we done having a conversation about entanglement? You've created left and right. You did it. So you're pretty much done in terms of surmising about what's happening in the rest of the experiment. So even without my explanation, the evidence should be so thin to you that you would say, well, prove it, because you're way short of that. The experiments are insanely complicated in terms of measuring these photons. It's just bullshit. Alright, now you want to believe it? That's your business. It's like saying, how do I explain the Bible? I don't have to explain it. It's a stupid storybook. It's a bunch of fables. Alright, it's nothing to explain. Alright, anyway. How do you explain photons, neutrons being bound in the nucleus? So you didn't use the word electrons. Well, a neutron has already been well established to be a proton and an electron. That's what it decays into. So if you just do the addition, neutron, proton, electron, and then you add another proton, well, what happens when you have the electron in the middle, okay, the thumb, okay, and the other two fingers are protons. Well, what happens if an electron's between the two? Well, the two protons are attracted to the electron, okay, less pressure. And the protons, essentially, you could argue, can't see each other. And so they can't repel. So you're not pushing two protons into each other. You're just providing a mechanism that allows the pressure to escape, quite obviously, or protons wouldn't be attracted to electrons. So I've done videos on the blue and red theory. There's two forces, two kinds of matter, two kinds of force, two kinds of interactions. One of the interactions is a reflection. The other interaction is a change in its polarity. So a force goes in that's an electron reflective force, and it goes out, okay, as a proton reflective force, or vice versa, depending on which one you hit. So the electron is a perfect conduit to dissipating all of the pressure that the proton would have with each other, because it's changing the force from a repulsive force into an attractive force in net. A force that pushes into a force that doesn't push. So there's not some strong force pushing protons together. There's an electron mitigating the pressure. So I'm sorry you have wrong answers, but your answers are wrong. Physics has made up a silly, weak, kind of incoherent, invisible, unmechanical theory, and you're believing it. I mean, not my bad. You're bad. So you ask these arrogant questions about how I explain something that really hasn't been proven at all. They don't have any video of the strong nuclear force, and again, it's built out of only one argument. This is as far as they could see. This repels this. Therefore, if they ever get close to each other, it's because some force pushed them. and no other explanation can be provided. Why not? Yeah. All right. Protons and neutrons being bound in the nucleus. Strong nuclear force. So again, the strong nuclear force is misnamed because it's really the weakest force there is, because the electron has essentially consumed the force by changing it into an electron force. Much stronger than EM, so whatever that is, electromagnetism, I don't know. So again, you're assuming a force merely because it takes energy to knock it over, but you're assuming it's on a good foundation and assuming there's not some other reason it happened. It's not, it's like just jumping to one conclusion when there could be lots of explanations for what happened, and actually increase over a certain distance instead of diminishing. So, that argument, in my opinion, has really absolutely no evidence. Okay, so that the strong force is stronger the further the protons are from each other. No chance, but whatever. Believe what you wish to believe. I would say you could surmise again. I won't draw it. I mean, you should be able to get it with me just visualizing it. But let's say the electron is very small and the protons are bigger, right? So in my scenario, from a distance, okay, the two protons are only weakly interacting, and the electron is doing the same amount of conversion. And as the protons get closer, you could sort of understand that the protons now can see each other more. So even though the electron's still strong enough to mitigate enough pressure that they still are attractive, you can understand that the force gets weaker as they get closer. So it's not that the force is stronger at a distance. That is, there's some force that's stronger at a distance. It's just that the effect is less effective the closer you get, just like an atom itself. An atom is basically, it's, again, my face is the proton, the positive nucleus. Now, the further I push the electron out, the weaker the force. And the closer I bring the electron, the stronger the positive. So it's exactly the opposite polarity at a distance, which is pretty significant. It's very significant in terms of arguing about how the force works. So obviously at a distance, atoms are negative if you're close to the electron, and if you're not close to an electron, then they're positive. It just has to do with your point of view, but whatever. How do you explain particle jets? I mean, whatever that even means. How do I explain a sandblaster? I don't know. Particle jets? What the hell's a particle jet? I mean, what is that? Do you mean real particles like electrons and protons? Or do you mean some kind of photons? Frankly, I don't know what you're talking about. All the stuff moving slower than the speed of light would be something I would call a particle, okay, in the material sense. It's matter. Anything moving the speed of light is not technically a particle, it's a force bit. Alright, so, but whatever. So how do you explain quantum entanglement? We did that. Yeah, okay. How do you explain? So, it's my obligation to explain. So they don't have to explain anything. They don't have to really show you anything. They don't have to have any good video of anything. And Stern-Gerlach is a good example. There's not a single video of somebody doing the Stern-Gerlach experiment. There's just pictures of this and pictures of that, but no real video of the actual experiment and actually changing the dials on the machine to see if you can change the shape of the... Nothing. Just absolutely nothing really of any value. But you believe. Okay. Why do you believe? Because they say so. That's all you got. How do you explain particle spin? There's absolutely nothing. The Stern-Gerlach experiment has nothing to do with anything called a spin, in the sense that even the physicists acknowledge that spin is just a property. It's a name they've given a property. It's not really something spinning necessarily. Now, the property is a dipole, which we know electrons aren't a dipole. Electrons aren't positive sometimes. No, it's just nonsense. They can't be a spinning magnet. They're not spinning. And if you spin something that is exactly the same on one side as the other, how would your spin be relevant? And how could spin be relevant if it was spinning in, like, say, empty space? It can't move in a direction because of its spin. I mean, there's no ether for it to drag on, to have friction with. I mean, it's just pointless. All right. How do you explain particle spin as physically demonstrated? So again, there's no physical demonstration of anything spinning. All right. In the Stern-Gerlach experiment. Okay, so a really underdocumented experiment. And right in the beginning, they're telling you we're sending silver ions through the experiment. They're not electrons. They're atoms. So positively and negatively charged silver atoms are going through the experiment. And you're telling me to explain why, when I put a magnetic field, I shoot them through a magnetic field, that some go up and some go down in a certain pattern, a little teardrop pattern? I have to explain that to you? Sorry, that's too silly. And the fact that it's teardropped is because there's probably more of them in different locations, depending on how narrow your gun is. So some of them go into the magnetic field in the heavy, strong magnetic field, and some go in the weak field. Depending on which part of the field they go in, depends on how much their momentum has changed, that is their direction, how much they've been bent in their path. But I mean, they're obviously polarized bits sent through a polarizing filter, so obviously they're going to create a pattern. So there's no idea that these are electrons. How are you detecting the spin of the electron on the silver ion? I mean, you're saying you're looking at a silver atom and you can tell which way it's spinning? I mean, get rational. Too silly. All right. I think they have the weakness of this evidence is so weak, again, and you're so arrogant. How do I explain how they wrote a 3 pigs story? So how do I explain that 3 pigs didn't happen? Well, all I can really go is to the credibility of the author. All I can say is, I can't prove the negative. I can't prove the fake. I don't have videotape. All right. I mean, I can only use the evidence that exists and the fact that they've interpreted the evidence. Again, somebody could blame missing socks. You put the clothes in the dryer and stuff disappears. They could blame that on gremlins. And then other people would suggest, there's a mechanical explanation. It fell through the filter. It did this, went through the crack in that thing. When it spins, there's some other explanation, and the sock is someplace. But you don't need none of this gremlin crap. And that's all they've got is gremlin crap. You're just following the scat, gremlin scat. There's no such thing. You're tracking mirages, and it's not my bad. I think you're bad that you're so illogical and you demand so little out of an explanation. You'll accept extraordinary with less than ordinary evidence. Because you really just want to believe. I smell the hint of gasoline in the morning. Yeah, it's like Apocalypse Now. But anyway, so I'll be back. Alright, back on the subject of kinetic energy and gravity, really, because that's where all of this went foul with the kinetic energy theory. Because of the fact that they have decided that because a way to measure a velocity at any particular time is just to measure how far something traveled, and in a unit of time. So you just measure the distance and the time, and you can tell how fast it's going. So it has a timed component, but they're focusing on the distance part, thinking the distance has something, the distance you move has everything to do with how the force gave you that ability to travel distance. So I'm simply arguing that there's two things in the universe: the force, and that's always moving the speed of light, and the matter, which has no ability to move at all. Boy, you can barely see that. But whatever. It's almost the end of the purple. Okay. Why am I doing that? I wanted an F there. Force. Okay. And matter. So matter is big stuff. Okay, no motion. The force is moving the speed of light. And all you're really doing is dividing the force over the matter. That is, the matter is sitting there saying, push me, and I'll go. So hit me with something. All right, and I will absorb that energy. I'll move less than the speed of light to another location, and then I can give back the force in some other direction, or I can, whatever, it doesn't matter. I release it. So it's just about being pushed. So you could just say everything's just shooting bullets or reflecting bullets. So the universe is full of little bullets, and they're just ricocheting through the matter, and with each ricochet they give the matter a little, they spend a little time pushing it. Some rule like that. And so when something has weight, okay, you're just saying how much mass is there for me to hit with bullets. So that's why matter, how much mass you have matters, is because it's how much capacity it is to even interact with the universe. And then how much of the pressure differential is there. So, one side of the universe pushes more than the other side of the universe. The matter moves where it's pushed, where there's more push, more incidence of being hit. And so, it perfectly explains gravity in the sense that it's just about how much mass you have to collect the pushing, and then how much of a differential is there. If I have a small piece of matter, then this is only 2 bits can hit me. If I have a piece of matter twice that size, well then 4 bits from this side will hit me in 1 second, let's say, 1 unit of time. Yeah, second. So that's all, it's not that complicated, right? 50 times the matter, well 50 times more of these 2's will happen, okay, because I have 50 times more capacity to receive that much more differential in the force. And so the heavier object collects more force in gravity per second because it's big. The small object collects less, but the proportions, the fact is it's the fact that there's what's coming this way and what's going that way. And you don't stop moving till you hit something that's not moving, something that's saying I'm going both, I'm getting pushed by gravity down, but I have stuff inside of me that bubbles back up at the same rate. So I've equalized the force, it's just in a different form. So the force is coming down here at the speed of light as little, ultramundane, rain, and the force pushing back is pushing back with boulders of matter, throwing boulders of matter at this matter. Okay, to create the opposite pressure. So the pressure isn't in exactly the same form, but the key point is it's pressure. It's just about pressure. There's pressure down, there's pressure up. When the pressure up matches the pressure down, you stop moving. You're still being gravitationally pushed. The pressure's still there. The pressure between you is still there. That's why you weigh something on the scale, okay? The spring is compressed by the unevenness in the pressure. The spring doesn't, collects the pressure. When you first hit the spring, there's very low pressure. And then as you start to get closer to the point where it's going to equalize, it increases. So it's very low pressure here. This feels little pressure when you first hit the spring. This is feeling almost no weight at all. It doesn't feel the full weight of your mass until it gets to some point where now the spring is also pushing back at the same rate as the ground is pushing back. And so those two pressures have equalized. And this shows you the net difference, your weight. but your weight is just showing how much pressure your matter creates when sitting in the gravitational field. And as you're falling, obviously there's nothing stopping you every second from collecting more and more of the consequences of that imbalance. So with the imbalance in 1 second would be a certain volume of extra bits of energy that have pushed you, and there's nothing that countered that volume, and so you just keep collecting more volume, and so your velocity increases, but the time is all that matters. How long are you in the force? And so, this is just, it's so elemental, and for you all to have jumped to the conclusion that somehow it has to do with, well, you fell 4 times further in the gravity, therefore you must have 4 times the energy. No, because you're only in the gravity, okay, twice as long, because of the fact that you're doing this, in the first second you only fell this far, or the first quarter of your falling process you only fell this much, and in the second quarter, the second 3 quarters, you fell this much, okay? And that happened in the same amount of time. So in 1 unit of time you did this, and in the other unit of time you did this gigantic distance. So again, comparing distance, when you're not accepting that your velocity is changing, you can't measure the energy of something if you ignore whether it's going faster or slower through the force it's collecting. And obviously you're collecting it. And so yes, it's only twice the energy. It's only twice the differential in force that you actually experienced, because that's only how long you were in the extra gravity. And if I halved your mass, obviously they're twice as long in the field, but at half the mass, half the collection, the bucket is smaller. I've used this rain bucket analogy. Gravity is just a rain. You're collecting it in a size bucket, and you can only collect it while you're moving. If you've equalized it, then you've lost what you collected. The bucket's empty. It's emptied by you hitting the ground and having an equal pressure compensate for all the water you've collected. Dry it up, so to speak. So, I've been over this so many times. I took some notes and I'm saying, well, maybe I can make something here that you could get. All mass has is the ability to be pushed. That's all your mass gives you. So again, your mass has no weight in space. And it's just sitting there saying, give my mass weight. Push me. So if I push you this way, then you'll go that way, and you'll hit something with a pressure, a weight. And so I've made the simple argument that the experiment to do is to find out how much weight, how much your weight changes as I drop you. So if I drop you from 1 inch, how much do you weigh? If I drop you from 10 inches, how much do you weigh? And that'll tell us exactly how much you actually, when we say you weigh, 150 pounds on the surface of the Earth, the argument is you're applying 150 pounds of differential in the pressure. You've collected 150, capacity, and the ground is pushing you back with 150 pounds of pressure. So you could argue it's 75 and 75. Well, don't really want to get into that. The two contributions creating the net product of the Earth pushing up and you pushing down. But it's more like, the gravity pushes you down and the Earth just eliminates that push. You are free falling. You're falling, and the Earth just keeps restoring you to the old position. So you fall, you actually move, but the Earth just restores you to this position. So then you move again, and it restores you. And each time it's restoring you, it's taking away your previous velocity. So you can't gain any velocity. But we could argue that the gravitational constant is essentially telling you what the velocity is per unit of distance. So if I can double your weight, by moving you up. So I take you and I lift you off the ground, whatever it is. So I don't know. I have to do this figure out how high do I have to go to double my weight, to double how hard I'll hit the spring. The spring compresses because of a weight or a pressure. So how much pressure is 300? Let's say if I weigh 150, how do I get 300 pounds on that spring? How high do I have to drop me from? And once I know that number, then you can make some argument that I can figure out the number that the Earth is pushing back up all the time. And that's the number you're actually moving down, okay, all the time in gravity. And it always is just the first part. You never gain the extra velocity. You just gain that first bit of velocity. So either you're going to be able to calculate the distance you move, or you'll be able to calculate the velocity that you move. But you are moving that when you're standing still in gravity, sitting in gravity on Earth. The fact is your matter is moving. It's just going both ways. It goes this way and then it goes this way in equal amounts at any one moment, because you are collecting the force, because you have a weight. So it's obviously you have something, as a force has acted on you, but you can't have weight without that. So, and then you can get into the argument that once you've doubled the weight, you could argue that that's twice the exposure to the energy, and it would be 4 times the height to do that. So you could say that whatever the pushing up force is, it's 1/4 or 1/2 of that force, 1/2 of that distance. So anyway, but yes, the fact that gravity is a time-dependent force. I don't know how many times I have to say it. I mean, that is so provable. And again, it's so easily proven just by the flyby thing. You're going to fly by the Earth. The faster you go, the less you get bent. And what does that mean? It's just basically saying the faster you go, the less time the differential between the Earth and space has to push you. I mean, space is creating more energy this way than the Earth is allowing to go back this way. The Earth is blocking it, consuming it, using it, whatever you want to say. So there's a differential. And the only thing that changes how much your path gets bent is how long you're in that differential. The longer you're in the differential, the more likely it is to hit the Earth. The less you're in the differential, the less likely you are to be significantly affected by that differential, because you ran through it really fast. So there's a hole in the ceiling. You run through the hole really quick underneath it. Very few raindrops hit you. You walk really slowly. You get lots of rain. That's the right answer. That makes sense. It fits all the evidence. I don't know. It's probably how Newton, Galileo, and Descartes actually looked at it, or saw it, or visualized it, or imagined it as a completely time-dependent force. How long you're in it matters. How far you're traveling is circumstantial. Lots of things can screw up your traction, so to speak. All that really matters is how much time you've given the force to hit you, and how big a target do you have to collect the force. I don't think I need to really. Maybe I'll do a more specific video and just try to incrementally going through some of this stuff. But those are obviously some experiments I'm going to do. I don't have a very sophisticated scale. I don't have, blah, blah, blah. An electronic one really won't do the trick for this experiment. But the idea would just be to, just drop things and measure what's that initial, because that's the only thing that matters. It's not a constant force when you're trying to measure its collected force. Its collected force is not the constant force. The constant force of gravity is just 9.8. You want to know what's the total amount of force it's collected. So you have to get the very bottom number, not what it comes to as a balanced number. You're not trying to ascertain its mass. You're trying to ascertain its energy. How much has it collected? And how far does the spring compress before the force pushing back up is equal to the force that pushed it down. And that's what you're really trying to find. Alright, so it's just amazing that these experiments haven't already been done. Somebody hasn't documented the dropping of an object on a scale to see how much more it weighs based on how high I drop it from. I'm just amazed that that's never been documented ever, apparently. Strange. If you can find it, please provide me a link, because it really is going to, it will tell the truth, that it's just about how long the pressure is being applied. Yeah. And like I said, other velocities you have aren't being, there's no constant supply of the pushing force. So all you have is what you can do instantaneously, in an instant, what you can provide as energy. And that's all you have. That's what momentum represents. I mean, the fact that, physics has basically perverted things so much that they actually think that every bit of energy happening in the universe at any one time is somehow being fed by some kind of gravitational field, and it's not. It's just collected. It's already been collected energy, and there's just a certain amount, and once you use it up, it's gone. There's not some pusher continuing to push. All right. Yeah, probably enough. All right. So we'll call it a video, and so this has been DraftPhysics.com. There's also DebatePhysics.com, but just so it's, again, strangely impossible to provoke anyone to engage in debate or conversation about these elemental functions of the universe. And all the other dissidents out there are just doing shows. They're not interested in being challenged or in doing any challenging in any kind of way, but to do it in some way where they don't have to worry about counter arguments. And so I just saw a video by that Distinti guy, and it was just such a piece of PR crap. If you join as a Patreon member, well, I'll let you know what my great ideas are months in advance. For $5 a month, you get to know everything. If you don't pay me $5 a month, I won't let you know anything about what I'm doing. And, all this bullshit about his unification, and just forget it. He's left the building, the reasonable building. So anyway, so they're all nuts is what they are. Unfortunately, most of the dissidents are demented. They're not just dissident. Anyway, so till the next time, and such, so forth and whatnot. Yeah, that's enough.